All right, welcome back to Introduction to Computer Networks at NTU. How are my students doing? I think you guys are probably doing well, okay? This is week 10, episode 18, okay? Yeah, I understand that exam number 2 is coming up next week. But given how you guys did for exam 1, I think you guys would have more fun than I would have expected, right? And in terms of other assignments due this Saturday, we have PA7 due. From what I can tell, PA5 and 6 seem trivial for you guys, which is good, okay? But the PA7 is going to be a little bit different. You'll be using the existing web server already embedded in Golang for this assignment. Okay, so this one will be a little bit different. It would definitely take more of your time, but not by much. Okay, some of you might be keen to observe how Poly assign the exams and the PA assignments and other homework assignments. I'm actually assigning them such that during the midterm weeks, the load is light. So you can balance your life a little bit better. And I hope that it works. Okay, but starting from now, because this is 2 weeks beyond the midterm week, we'll have more quizzes, and the things that we'll be discussing will get more technical. So more attention will be required. You will see that actually today. All right. And let me just say hi to the rest of the class that just popped in. Hi, Bo Yu. Hi, Ying Xuan and Yu Qi. Good. And you know what? Today, we're going to start with the quiz. Okay, so this is quiz 26. All right. Let me see. Yeah, maybe we should just go to the PowerPoint space so that probably can describe what the quiz was. All right. So last week at the end, we started introducing this problem called congestion, right? And when congestion happens, things can be really bad, right? So we would have a prolonged delay, and we have packet drops, and sometimes the delay can be unnecessary. Sometimes the drops can also be necessary. To the extreme, when there are too many traffic going on, sending more is actually less, okay? So that will be the situation that is the least, okay, that you want. Okay, that is why in this quiz 26, what you're seeing is everyone has experience of traveling on highway, okay, especially during the holiday seasons, right? The more car there are on the highway, the slower, okay, the traversal. So, yeah, it's a serious problem. And how do we address this problem? Okay, so again, you guys will be actually challenged, okay, from your experience in the past to see the nature of congestion and how existing systems that you're familiar with addresses the congestion situation, all right? So in quiz 26, you guys are asked again to role play, and this time role play the Uber driver, okay? And you serve this line very frequently between the city center, Taipei city center, and the Taipei airport. And highway number 1 is the main route taking customers from the city center to the airport. Okay, and today, unfortunately, as you take your customer to the airport, it's badly congested. You've observed this. Okay. So Q1 here asks something that's a little bit more general. Can you name a couple reasons that cause congestion on the highway? Okay. Q2, how do you inform your fellow Uber drivers so they don't take this route that is already congested? Okay. So your friends can be taking some other routes that will be able to take the customers faster to the airport. How about that? Good. And for this quiz, okay, so learn from your past experience. You guys have 6 minutes, okay, to think this through and input your solution. Oh boy, let's see. Okay, if you go to the Discord space, I see already Team 12 posted the solution. But you know what, guys? You have 6 minutes. Let's start counting time. Oh, okay. Oh, wow. All right. Yeah, I see you guys know well about congestion. Yeah, having car accident, that is very common, the cause. And traffic jam, of course. Yeah. Busy holidays, big events, car accidents. Oh, bad weather, right? Bad weather is another major reason. And of course, rush hour. Okay, so a period of time that everyone travels. For some reason, human activities synchronize, in particular during the weekdays, right? Because we work a certain period of time and then we rest. And it seems that given that humans are social animals, we work at about the same time, so that it's easier to find people to communicate with, right? Oh, okay. So Team 2 says that use the building Uber app, right? So you can then message each other, or using some simple buttons to click and indicate the traffic condition. Too many cars running on the highway at the same time, right? So this is also how we explain what congestion is on the internet, right? If we send too many data at the same time, then we run into congestion. Because there's always like a volume that a road can accommodate, or a volume a network connection can accommodate. When we exceed that volume, then congestion. And how do you inform? Radio. Okay, so that's another way. Let's see how you guys say things differently in terms of how you notify each other, right? Signal location through shared access map. Oh, okay. So I think this is a little bit similar what Katie was saying, right? But this can be like a map on Uber app, or it could be a map on Google app, or it could be a special app. I think it's some time ago I used an app that was actually popular, but I stopped using it. Okay, if I recall what it is, I'll let you guys know. I think you guys will also recall the same app. And let's see. Car accident, wait for the stone tiger to pass and wait for the white dolphin to pass. Yeah, so especially in countryside, right? So up on the mountains, we can see some animals trying to cross. Yeah, so we stop and wait for them. Camera. Oh, okay, so this solution is a little bit special. Installing a camera at places the congestion happen more often. Then people from remote location can actually tune into these live cams and observe what's going on. And you know what? There are many of these live cams around in the city. Okay, major transportation systems. So this is certainly something that a certain solution that I see more common. Phone call. Yeah, I think this is sort of isomorphic to the using radio solution, right? Earlier we see another group saying, hey, just use radio. And phones are essentially radios. And let's see, Team 13. Mark the road is congested on Google Map. Traffic flow surpasses the throughput. And highway may be the main connection. Yeah, so if this is the main connection and there are so many people needing to go to the airport, or other cities nearby the airport, right? You can imagine it's congested there. It's when it's a popular route. Okay, that increases the chance of congestion. Tell your friends, then your friends, okay. So you tell the friends and maybe the friends will spread the words, okay? And see, Annabelle, could be rush hour. Many people trying to go and pass. Yeah, or an accident. Yeah, I think during the normal hour, not the rush hour, the chance is high that there's an accident if you run into a congestion. Message other drivers and the other drivers messages their friends. Just spread the words, right? I guess. Okay. So you can see that, through radio, social media, that is when you're stuck on the network and if you want to inform people, okay, then within the network, you somehow send something out, okay. But using a built-in live camera or having other people intended to go to the airport from the Taipei City Center to check Google Map, that is more that these guys observe from the ends, okay, before they go on, get stuck in the network to discover that there's a condition, okay. So you see that there are kind of two classes of ways, okay, for the people going on the highway to see whether they should go or not. So you inform your friends potentially in two classes of ways, okay. So I see team 18, 16, Felix. I think you guys have probably come up with similar ways in either one of the classes, right? Group chat. And this is actually you trying to send signal out, okay, from within the network. Using the central network to inform others, okay, of condition. So a central network, so this is more like the ends, okay. The fellow Uber driver, instead of getting the message from you, they somehow discover there's a condition from the ends, okay. And let's see, 26 for Uber apps, there should be a report system. Yeah, so this solution then it's a little bit of a mix of both, right? So you actually give a signal, but you actually tell some server more central, and so that the other Uber drivers would discover by logging into the system instead of getting the message directly from you, okay? So it's a mixed solution in a way. Radio, you spread things out, right? So this is probably from within the network. Get information in the social media. This is to get information from the ends, okay, before they go on the network. Report to police progress. Oh, okay, so this is also, right? From within the network, you report to some central units so that the fellow Uber drivers not getting message directly from you, but at the end, they discover there's a condition somehow. Good. Tell others through messages and mark the traffic. Okay, so hey, Team 14 is saying both ways, right? Getting messages directly from me within the network or getting from some apps that somehow collected information, okay? Infer the information. And so that the Uber driver at the end can discover there's a condition and make decisions at the end. Good. Guys, so essentially two ways, okay, to discover condition, okay? And you know what, guys? Yeah, we do have two approaches. So this video coming up, 4 minutes, 15 seconds, you see an overview of the two approaches and a little bit more detail about the first approach, that is end-to-end. With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a condition is to what? Just slow down. And therefore, the two key design elements in a condition control mechanisms are these. First, detecting when a condition is occurring. Second, notifying the traffic sources that's causing the condition to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach, the other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting condition, informing the traffic source to slow down. Network-assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there's a condition occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss,
Or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a condition inside the network. So that is, observing from the loss occurring, inferring there's a condition. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for the packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that, also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network in the meantime, not being too conservative, too slow sending the data out. Okay. And this is actually rather hard to do for the end systems. After all, they're actually at the very edge of the network. The congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss. If there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right? If there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah, that is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting the signals of congestions, then that's slowed down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay, pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based condition.
Yeah, so it's an end-to-end based condition control. And from the video, you actually see that not only there needs to be a way to discover a condition, or the network somehow need to let the ends know that there is condition, but also that at the end, we need to also know how much the network can accommodate next. So you need to guess a little bit, okay, what is the right sending rate, and decide whether you take your chance, isn't it? Now, let's take a look at the other approach, that is actually the network-assisted approach, before we go on to talk about how TCP decides when to send more and when to send less. Okay, so the second approach, net-assisted.
The network-assisted approach. Okay, so in this approach, routers will be doing the congestion detection. But how? Well, we also need to observe something, but this time we could actually observe something that's very directly related to congestion. That's the queue size. Okay, so this is the queue of these packets gathering at the entry point of the router. Okay, so congestion is this: sources of the traffic sending data too much, too fast into the network. Inside the network, we have these routers, right, handling packet forwarding. If the outgoing rate is slow and incoming rate is high, then these packets will need to be buffered temporarily, okay, at the entry point of these routers. And therefore, they get a chance to wait for their turn to go out on the outgoing link. If the outgoing rate is slow, incoming rate is high, queue gets long, and free buffer space gets small. Right? So queue size or free buffer space, okay, changes of these, okay, are good indications of a congestion occurring. Now, routers, however, are the devices in the middle. Okay, how do the routers inform the sources so that the sources know that they need to serve down? Yeah, this is the way it's done. Okay, Okay, so there are these bits, special bits, okay, inside the packets. So when these packets travel through a router, and the router is so busy, queue size is so big, or free buffer space is so small, these bits get turned on. Okay? And when the packets arriving at the receiver, receivers can check these flags or check these bits and then inform the source of the data, the sources of the packets. Now, in internet, okay, the TCP/IP protocol suite. Okay, yeah, let me explain. Yeah, TCP is actually a transport layer service. Okay, but sometimes we also call the transport layer the TCP layer. IP is actually a network layer protocol, and therefore sometimes we actually refer to the network layer as the IP layer. So TCP/IP here is actually referring to the internet protocol stack because the transport layer is running TCP. The network layer is running IP. So these two are the very typical classical protocols that are running, okay, supporting the operation of the internet. So in TCP/IP or in internet, we have these special bits, and we call them the explicit congestion notification bits. So when the router inside the internet, the queue size gets large enough or the free buffer space gets small enough, we set the ECN bits on. And therefore, the receiving end, the TCP receiver there, seeing the ECN bits on can inform the source to send them. Now, that is how the routers in network-assisted approach detect congestion and notifying the source of the congestion. What's nice about this approach is this. The routers there observe exactly how much free space there is, okay? And dividing by the number of flows that's going through, number of connections that's going through, hey, routers can also be more explicit, telling the receiver to inform the source. Now, set the sending rate to this size. Set your sending window size to a particular size, such that we will not be overwhelming the router buffer space. Just like the flow control mechanism, right? Receiver there observing the receiving buffer, depending on how much is free, set the sending window size accordingly, and voila, problem solved. Receiving buffer will never be overwhelmed. Similarly, the router's receiving buffer here will never be overwhelmed.
Yeah, so if it's the network-assisted approach, usually it's easier to get a precise estimation of the congestion level and easier to make a decision whether you go on or not. Good. Now let's move on to this issue about finding out what's the right sending rate next if there's a congestion. Okay. So it's actually a guessing process. As Polly mentioned in the two videos that TCP is actually taking the end-to-end approach. Therefore, there's some guessing game that we need to play. And before we talk about exactly how TCP does the guessing, that's exercise from our experience or from this game show quiz, okay? And see if you guys can come up with something effectively yourself, okay? Polly has already introduced the quiz last week, so maybe we can quickly jump to the discourse space. Guys, are you ready? Yeah, there are two stages, right? In stage one, Polly would just post one item. So here are the specific instructions, okay? You don't need to join the Google Meet session for stage one. And Polly will post the merchandise on the channel. Each team is given 1 minute to discuss. Okay, guys, just 1 minute. And then one member will type the team number right before your estimate. And there's no editing after that, okay? But if you really need to change, you will need to put on another post, okay, instead of editing the previous entry, all right? And Polly will post the true price. Okay, if 2 or more teams are the closest and below the actual price, we'll take the earlier post, okay, that is the closest, okay, to the true price. And the team, okay, with the earlier post with the closest price will be the winner, okay. And guys, the prices of all the items Polly will be posting on the channel will be in NT dollars, so your guesses will all be in NT dollars as well, okay. And Polly has tuned the price up and down a little with some random margin, okay. So that is saying that you need to know the rough range to help, but you also need to be lucky to win stage one, all right. Now the winner of stage one will enter stage two, okay. You guys will need to, the winner will need to mute your YouTube live stream first to avoid echo. And then join the Google Meet session. Okay. A merchandise will be posted on the channel. Okay. And Polly will give you a few seconds to breathe before we start. And then Polly will start the timer here. Okay. And you have 30 seconds to guess. And for each of your guesses, Polly will say too high or too low, and you would adjust your guess until the price is exactly right. Okay? And I hope this is clear. Oh, by the way, Ivan asked whether the price is going to be integer. Yes, it will be integer. Otherwise, this might take forever. All right? Good. All right. I hope that you guys are ready. So let's get the first item up. All right. It's a keychain. Okay, it's a Labubu keychain. All right, from the Monster series. All right. So this is the item you guys will be guessing. You'll be given 1 minute. So Polly will be clocking you guys. So let's set it for 1 minute. All right, so start counting time, 1 minute. Guys, you don't want to guess too high. If it's beyond the actual price, you lose your position of competing. Don't forget your team number. Okay, according to my clock, you have 30 seconds remaining. Oh, okay. Yu Zheng, you obviously has no idea about the value of these Labubu keychains. Okay. Oh, Ray. Smart. Zheng Nian, smart. Jiadong, I think you're close. Ethan, yeah. Oh, okay, Andrew, good strategy. Guys, time's up. All right. Time's up. Okay, so, I give you a few seconds delay. Very good. So let me just add stop here. And here's the actual price. So let me post the actual price. Oh, Xingwen is still posting. Oh, it's okay. Yeah, as long as your guess is there, you're fine. Yeah, the actual price after Polly's adjustment a little bit, just a few $10 is 672. So let's go back and see which is the winner. 672. Okay, anything above 700 is already too high. Oh, Sparrow, you have a good chance. 550. You're so far the closest and below. 672. 672. Okay, Zheng Nian is a little bit too low. So you guys are all too low. 672. Okay, Annabelle, you're just a little too high. Oh, you're close. Oh. You know what? Hey, we have a winner. And that's Sparrow. Congrats, Team 6. Okay, you're up for stage 2. So mute your YouTube session and join me here. There you go. Congrats, Team 6. Okay, I hope you're prepared. You don't need to turn the camera on, but you do need to have your... I know, guys. Those who guess 700, you guys are very close. Just a little bit higher than the actual price. Okay, yeah, let's give Team 6 1 minute. There he is. Emit. All right, Sparrow, can you hear me? Hi, but can the class hear you? Guys, can you hear? Oh, well. Let me see. All right. Yeah, I think the class can hear you now.
Now, okay.
Okay. Yeah, so I just restarted the audio. I think the class can hear you. Okay, let me know. Class,
Okay.
can you? No, cannot hear. Can you hear? Can you hear Sparrow now? All right, good. Okay, all right. Good. Let me post the item for you, Sparrow.
Yes. What?
Let me
Excuse me.
see. Yeah, so let me
Yes.
post the item now.
Okay.
All right. Hey, it's
Inside the Discord space.
yeah, it's on the Discord space. Okay, so the
Okay.
rest of the class can still see it. It's still a Labubu item, but this one is gigantic. I think it's this big. Okay, this big. Okay, it
Okay.
does. It says in the description, 2283 inches high. Okay.
Okay.
All right. This one is pricey. Okay.
Okay.
And you don't need to worry about going beyond the actual price.
Okay.
But the challenge is that you have only 30 seconds.
30 seconds to guess until the
The
last digit, like the
Yeah, until
个位数,
exact right.
right? Yeah. Okay. Ha.
Okay.
Yeah.
Wait. Polly needs to know the actual price as well before giving you the feedback. Okay. Hey, I'm also nervous, guys. Okay. Okay, you're all right. Okay, are you ready, Sparrow?
Yes. Yes, I am.
Okay, let's start counting time. The time
Okay.
starts now. Start.
Okay. 2000 NTD.
2,000 too low.
Yes. 2000 kilo is 3000.
3,000 too low.
Low. Okay. 4,000.
Too low.
Oh my god. 6,000.
Too low.
8,000.
Too low.
Okay. 10,000.
Too low. 10,000 too low.
15,000.
15,000 too
15,000.
high.
Okay. 13,000.
Too low.
Okay. 14.
Too high.
Too high. 30.5 thousand.
Too low.
13.5 is too low, so 13.75.
Too low.
Too low, so 13.8.
Too low.
30.9.
Too low.
13.95.
Too high.
13.93.
Too high.
13.92.
Too high.
13.91.
Too high.
13.905.
Exactly.
Okay.
But no, it took you 1 minute. Okay. But very nice try. It's challenging. But hey, when I say too high, what did you do? You lower the guess. And when I say too
Yes.
low, you higher the guess. Okay.
Yes.
Well done. You did not get
Thank you,
the
Polly.
guess right within 30 seconds. Okay, but you get
Yeah.
the consolation prize. You get 10 extra points on top of the participation 5 points. So congrats, Sparrow.
Thank you, Polly.
No problem. Now let's go back to the class. Guys, did you get the idea? It's exciting, right? So how about you guys get another chance? All right. So let's play this game one more time. We have just 10 minutes left, so we need to go a little bit faster. All right. So let me put up a second round, okay, of the game. So let's try guessing the price of this item for stage 1. Oh, by the way, the Labubu price is 13905. Okay. Okay, it's a Caesar. Okay, guys, you have 1 minute to discuss, and I'm counting the time now. Okay. Guys, what is the price for the Caesar? Okay, the closest but not beyond the actual price gets to enter stage 2. This one is easier. Okay, Caitlin, good sense. Guys, 10 seconds remaining. All right, time's up. Okay, those who have not yet posted the solution, do it as quick as possible. And here is the true price. 260. Okay, do we have a winner yet? 81, 300. Okay, this is higher. What the? Team 16. This is exactly right. All right, let's see if there's another team that gets 260. 169. Sparrow, you're close again. Oh, team 5, you are also close. Okay. Oh, Ethan, 250. That's very, very close. Yeah, I think we have a winner. And the winner is 16. Yuzheng, are you ready? Yeah, turn off the YouTube live session, the volume, turn that off, and join me here on the Google Meet. So maybe I don't need to turn on the video. Or maybe. How did you get 260? Wow, amazing. All right. Okay, there is Yuzheng. All right, Yuzheng, are you ready? Oh, I think you're ready. So let me pose the item you need to guess. Oh, this one. Let me see if I can come up with something that's a little bit easier for you to guess. How about a monitor? Yeah, this is a 32-inch monitor. All right, ultra sharp. Okay, good. Wait. Let me set the timer. All right, Yuzheng, let's begin. Go ahead. Say the price. 10,000 too low. 10,000 and 5,000. You mean 15,000? Too low. 20,000 too low. Too high. Too high. Too low. Too high. Too low. Too low. Too high. Go ahead. Too high. Too low. Too low. low. 55, 65, too low. 67, too low. 68, too low. 'Too low. 'Too low. 'Too low. 'Too high. 80, very close, but too high. Exactly right. Okay, so again, so this is longer than 30 seconds. So you get a consolation prize. Okay, 10 points extra. But I think from Yu Zheng's case, I can see that you try to guess kind of some number in between. Okay, the too high and too low, that is the closest to each other. All right, thank you, Yu Zheng. Yeah, it gets nervous. Polly is equally nervous. All right, so hey, you get a rough idea, and you know what? TCP is also guessing this way. When it's too high, it will lower the sending rate. When it's too low, it would higher the sending rate. The question is, how does TCP know that it's okay to send a higher rate? Okay, what is the signal of too low? What is the signal of too high? Okay, so there's still time. Let's play this video. And you will see how TCP adjusts the window size and what is the signal of too high and too low relatively for TCP. And the mechanism is called AIMD.
And we'll take a look at an example of an end-to-end based approach, TCP's condition control mechanism. And TCP does it this way. The sender will increase the sending rate gradually if there are no packet losses detected. But as soon as there's a packet loss, we drop the sending rate drastically. So point number one here, packet loss is used as an indication of network congestion in TCP. Point number two, TCP is actually implementing a trying, failing process to discover what is the proper sending rate. Now, by sending rate here, I'm adjusting. In TCP, it's implemented this way by changing the sending window size. You see that the sending window size is a limiting number of bytes we can send out within one round trip time. Therefore, increasing the sending window size is increasing the sending rate. All right, the exact process of doing the trying and failing is called the additive increase multiplicative decrease, or AIMD to be short. So AI describes the increasing process of the sending rate. So this is done by setting the window size and such that it increases one packet per round trip time. And the decreasing part is this, cutting the window size to half of it, okay, after detecting a packet loss. So you see the increasing part is slow and linear. The decreasing part is drastic, multiplicative. So additive increase, multiplicative decrease. Okay, linear increase, multiplicative decrease. So if I show the sending window here over time, we'll see when there are no losses, the window size is going to grow linearly. As soon as we hit the loss, we drop the window size drastically to half of it. So additive increase, multiplicative decrease. So each of these AIMD episode looks like a sawtooth. And that is why people often say TCP's window size change over time shows a sawtooth behavior. One thing I want to add is this. We say we increase the window size by one packet per round trip time, but TCP sequence size is counting data by bytes. Window size is therefore also counting the maximum amount of data we could send out by bytes. So what do we mean by increasing the window size by one packet? That doesn't make sense. How do we implement that? Yeah, so the fact in the implementation, what's being done is to increase the window size by one maximum segment size. Okay, so MSS here, if it's configured to be 1460 bytes, then the window size is incremented by 1460 if there's no loss detected within the RAM. And this is actually related to the second point I want to stress. Yeah, you see here, the full name of the sending window is no longer WND. Right? It's actually called the congestion window size, CWND. Because the sending window size is dynamic in TCP, and it's actually controlled by the congestion control mechanism. That's why the window is now referred to as the congestion window. And this is TCP's process of trying to probe and discover the available bandwidth. Now let's bring up the diagram we used to explain TCP. Now it's counting bytes. Now each of these is what? A byte. If we'll be generating a new packet, then we'll be using the byte stream number here as the sequence number of the new packet. Right? So what you're seeing here is I'm updating the diagram such that this term here is no longer WND, the sending window size. We are now calling it the congestion window size, okay, because this here, okay, CWND is dynamic. It can be large or small. It's no longer a fixed size. And how large it is depends on how the network is smooth. How small it is depends on how bad the network is congested. And the quantity CWND here limits the number of bytes there can be between the last byte sent to the last byte act. Last byte act. So green here are counting the bytes that have been sent and have been act. So the last byte act is the last screen. Yellow here are the packets sent or the bytes sent but not yet act. So last byte sent is here, the last yellow. Okay. So last yellow, okay, subtracting the number of the last green. That means the number of yellows. Okay, so CWND here limits the number of yellow bytes there can be at best. Last, so we say TCP's congestion control is done by controlling the sending rate or changing the sending rate to discover what is the right one. Okay. We already mentioned earlier that is actually implemented by changing the window size, changing the congestion window size, because the sending rate is essentially the congestion window size divided by RTT, because within a round trip time we can only send these many bytes.
All right. Hey, so TCP's way of discovering what is the right sending rate seems easy now. So guys, tomorrow morning we'll continue to talk about TCP's congestion control mechanism. From last video, you see that the reliable data transfer mechanism and the congestion control mechanism actually intertwine, right? So window size, in order for TCP to do reliable data transfer, is actually determined also by the congestion control mechanism. Good. So you see, as complexity is picking up a little the later half of the semester, but I think you guys will do fine. So I'll see you again tomorrow morning, and that's all for today. Bye. Okay, bye guys. Okay, congrats to Sparrow and Yu Zheng again. Wow. Okay, bye.